Good day, everyone, and welcome to our monthly webinar here with CWNP. I'm Tom Carpenter, the CTO here at CWNP, and today we have a fundamentals webinar. We're going to be talking about antenna selection for Wi-Fi deployments. Now, in this process, we'll get into some more detailed information as well, but the primary focus here is to help people understand one of these fundamental and important concepts in wireless deployments, because today, it has become very common to just assume that you can use APs with internal antennas and use them for anything and everything. And the reality is that there are some deployment scenarios, quite a few actually, that can benefit greatly by using APs with external antennas. Of course, we all know about bridge links, and we'll talk about those toward the end briefly, but the main focus here is understanding antenna propagation patterns, understanding how antennas radiate the RF energy such that you get the coverage that it should provide, and therefore how to select the better antennas for different deployment scenarios. So this webinar presentation will be archived at the CWNP TV YouTube channel, so you'll be able to go out there within 24 hours, usually within a couple of hours of the webinar, and you'll be able to see the archive of it. But I do want to point out something that's a little different about this one. So Exceltex Solutions has offered all of those attending the live webinar today the opportunity to get a free antenna from them. So there will be information at the end of this presentation that gives you that information. So you want to make sure that you jot that down, because that will not be in the archived recording at CWNP TV. So if you happen to be viewing this later at CWNP TV, you will not be able to take advantage of that opportunity because it is only for live attendees. But make sure if you're here, you stick around till the end, and you can get that contact information to be able to get your free antenna selection from Exceltex Solutions. And with that said, the topics we're covering today will include basic antenna functionality and specifications, knowing how to look at the antenna specifications documents and understand the intended use of the antenna, the propagation patterns of the antenna, and things of that sort. We'll talk about the general antenna types, the issue of internal versus external antennas. We'll take a look at some different ways to visualize coverage patterns, and we'll talk about bridge links. So that's our topic set for the day. Our goal is 30 to 40 minutes for the main presentation. Then we'll have a Q&A period at the end as well. During that Q&A period, on the screen will be the information about the Exceltex Solutions offer. So you'll want to make sure that, again, you stick around for that, write down that information at that point in time, or take a screen capture of it, and you'll have that information to get your free antenna from them. So first of all, the first thing we want to talk about then is antenna functionality and a basic understanding of antennas. So the antenna is not really an intelligent component in most cases. That is to say, it doesn't make any real decisions. It doesn't do anything special. It just exists. And by fact of its existence at the right place in a radiation chain, it emits RF energy into space. So it is not so much that the antenna is making any kind of decision. The person that makes the antenna decision is you, and you have to make the decision about the right antenna for the right deployment type. So antennas, you could say, are stupid. They don't really know how to make any decisions. They're simply going to do what they're engineered to do by the laws of physics. So what they do is they take a received RF signal and they generate these electromagnetic waves based on the signal that they have received. So in the antenna chain, we have two terms that are used. We have the term of the intentional radiator, and then we have the term that is called equivalent isotropically radiated power, or EIRP. This is some fundamental stuff about wireless. And so the intentional radiator can be said to be everything up to but not including the antenna. So if you have cables, if you have amplifiers, things like that in chain from your AP or bridge to the antenna, everything up to the point where the antenna is connected is the intentional radiator. In other words, it's a device that is intentionally radiating energy. The EIRP is the actual radiated strength or power coming out of that antenna. And so the phrase might help you understand it a bit by knowing the parts of the acronym. Equivalent isotropically radiated power. The output power that we're getting in the intended direction of the antenna is compared to an isotropic radiator. So what is it in equivalence to an isotropic radiator, hence equivalent isotropically radiated power? And of course, we measure antennas in a very specific metric called dBi that we'll talk about a little bit later on. So they simply radiate the energy. They, of course, also receive waves as well, right? So it passes by the antenna picks that up, and it goes down through the cable. Again, the antenna doesn't intelligently make a decision to pick it up. It simply happens by nature of physics. And so it picks that up, and that signal or energy goes down the wire and eventually gets to the receiver through filters and other potential components. And it is those components that are intelligent. It's those components that make a decision as to whether this is a signal or if it's just some type of energy that is in the space, maybe from an unintentional radiator or from an intentional radiator that is not compatible with that particular radio. So the point is that antennas don't make decisions. They just do what physics dictates that they do. That's the first step to understanding antennas. The second thing is understanding active versus passive gain. So all antennas have gain. We simply are unable to create an actual isotropic radiator, and so therefore antennas have some level of gain. And that simply means that they radiate the RF energy in a particular direction instead of radiating it equally in all directions. So they have what is called passive gain. Passive gain is simply that gain that occurs by the nature of physics and the design of the antenna, which says that that antenna is going to radiate in a particular direction. Some antennas have higher passive gain than others. So if you need to create a long-distance bridge link, for example, you want an antenna with very high passive gain. In addition to passive gain, we have active gain. This means we're actually adding RF energy. In order to do that, you have to have an amplifier, or of course you could turn up the power on the AP, but we generally call that the output power and not necessarily active gain. In most cases, when we're talking about active gain, we're talking about an amplifier in path between the AP or bridge and the radiating element, the antenna, the aerial, if you want to use a different term from a different wireless space. So the point is that active gain is added through amplifiers, and passive gain is simply what antennas do, okay? Now, we also have to understand the difference between using one antenna and multiple antennas. First of all, with a single input, single output system, or a SISO system, we have one transmitting antenna and one receiving antenna. Even if the device has multiple antennas, only one is used to transmit and receive in a SISO system. So if it has multiple antennas, it might be using them for diversity or some other concept, but in most cases it's diversity, and the point is to be able to receive the RF signal on two different signals, or on two different antennas rather, and then choose the best antenna. So we can look at the received preamble. That's the early information that comes in on the antenna before any actual frame information is received. And that can be used then to select the best signal and therefore the best antenna. And this is sometimes used in older devices, and it can still be used in newer devices today when communicating with single radio systems. A multiple input, multiple output system, or MIMO system, actually transmits simultaneously and receives simultaneously, if the receiver is MIMO, on multiple antenna chains. So you're going to have radios that can transmit different signals at the same time. And in this case, we get more throughput, more higher data rates because of the fact that we're splitting our bits into multiple streams and sending them out simultaneously. So therefore, we get higher data rates and therefore in the end higher throughput in an environment that supports MIMO well. So these are some of the fundamentals to start with. Let's get into some specific antenna metrics. First of all, how do we measure antenna gain? Antenna gain today is measured in dBi for the most part. Now, there's another measurement called DBD that you don't see much anymore. It was comparing an antenna's gain to a dipole, and we don't really see that as much because it was just this arbitrary thing that really didn't provide any significant value over dBi for most scenarios. So dBi has become the de facto standard for reporting the gain of an antenna. And what it is it's the gain of a real antenna over what a virtual or conceptual isotropic radiator would be able to do. So an isotropic radiator radiates out in all directions, not just in a circle around it, but up, down, outward, in all directions, spherically, in the same level. However, antennas don't do that. Antennas have a place at which the signal is input to the antenna, and it is therefore not possible to actually radiate equally in all directions. The closest we can get to it is a very low gain omnidirectional antenna in most cases. So what we do then is we compare the gain of the antenna to what an isotropic radiator would do. And in an attempt to visualize that, we have here a 2 dBi antenna, and we have superimposed the point at which we had 50 dB, neg 50 dB of signal strength if it were an isotropic radiator. But we can see that at that point with this antenna, we have neg 48 dB, and the neg 50 dB point is further out. Now, this is only for visualization, and you're not necessarily going to see this exact thing in some kind of a real-world implementation. The point is just to conceptualize this concept of dBi and help you to understand what we're comparing it against. So by superimposing what the isotropic radiator might look like over what the actual antenna looks like, you can begin to get a feeling for what we're actually measuring with dBi. So the goal here is to say, what does this antenna do different or in comparison to an isotropic radiator? Now, the gain is in 3D space, and so while you might have gain in one direction, you'll have loss in another, and we can see that here. In this superimposition, you can actually see that vertically, we have less energy above and below our antenna, but horizontally, we have more energy further out over the isotropic radiator. And this is going to be dictated by the kind of antenna. And so if I have a parabolic dish, for example, then I'm going to see most of the energy going out in one direction from that antenna. And behind the antenna, above and below the antenna, I'm going to have very low output power is what it's going to appear to be. Now again, remember, I don't have any more RF output power than what I'm putting into the antenna. I'm simply focusing that energy and directing the signal in the way that I want it to go. And we have here an example of an omnidirectional antenna, which of course is what's common for standard indoor AP deployments when we place them relatively central to the coverage area, generally speaking. So this is what dBi is all about. It's all about comparing the antenna's actual gain to that of an isotropic radiator in the intended direction of propagation. We're not usually as concerned about the loss of output power in the unintended direction of propagation because we're selecting the antenna based on where we want the energy to go, right? And so our interest, our concern is what gain am I getting in the direction that I actually want the energy to go. Now, when you're looking at antennas, you're going to see antenna specifications. So this is an example of our 2 dBi antenna that we've been looking at. And you see some of the basic specifications for such an antenna. And the key things to look for are, first of all, the frequency. And here we're talking about the operating frequency range. Where is it designed to function? This one happens to be designed for 2.4 gigahertz. We see 2402 to 2495 megahertz, which is equivalent to the 2.4 gigahertz band. So this is a 2.4 gigahertz antenna. That's what it's designed for. And that means it's going to work best when you use it for 2.4 gigahertz. And that is therefore how it is optimized in its design based on the length of the antenna and the length of RF waves that work in the 2.4 gigahertz band. All of that comes together to form an optimally designed antenna for that operating frequency range. You'll also notice the resistance or the impedance level that we have here is 50 ohms, which is pretty standard for wireless LAN gear. There is the voltage standing wave ratio, or VSWR, which here is 2:1, and this is letting you know what that is, and you want it to be a lower is better, right? So for example, 1.5:1 is better than 3:1, right? So this is a lower is better metric. And then of course you have your gain. This is going to tell you what your gain actually is. It is also important to note the connector type. This happens to be an RPTNC connector on this antenna because that's going to determine if it will connect to your access point or to your cable connectors. And so we need to make sure that we understand the connector type. Of course, there are converters, adapters, pigtails, different terms they go by that can be used to connect. But every new connector you add in the chain from the radio to the antenna does incur some level of loss. So that's important to keep in mind as well. And then you're going to see the beam width. The beam width is telling you information about the radiation pattern of the antenna. Even without looking at charts, which we're going to talk about here in a minute, even without looking at charts, it already begins to tell you something. So notice the horizontal plane beam width is omnidirectional, which means that out from the antenna horizontally. If you're looking at this antenna upright in front of you, just like it is here on the screen now, then it's telling you that going out left and right, but horizontally all the way around it, it is going to radiate equally in all directions around it. Now, we know when we look at antenna charts, for example, that actually measure this, that it's not necessarily equally in all directions around it, but fairly equal. So you'll usually just see either omnidirectional or 360 degrees or something like that. And then 70 degrees is the vertical beam width here, the E-plane beam width. So this is up and down. If you're looking at it and you're seeing the RF waves propagate out, if you could actually see it, what would you see as far as the height of the RF wave? Well, the answer to that is it's going to get higher and higher as it goes out from the antenna, right? Because it is at some degree of propagation. So it's going to go upward as it goes outward, and it's going to get taller vertically, if you want to say it that way. But it is 70 degrees is what we're looking at here. And so with a 70-degree E-plane beam width or vertical beam width, what we're seeing then is this is a fairly low gain omnidirectional antenna. Higher gain omnidirectional antennas will have a lower degree in E-plane beam width. So this is actually a pretty standard dipole kind of antenna is what we're actually looking at here. So these antenna specifications, they can start to help you understand it, but there are visualization tools that help us as well. Let's take a look at a visualization tool that's actually available in a software program from IBWave called IBWave Wi-Fi, and it is a site survey, a virtual planning tool that helps you to plan or design a network based on algorithmic propagation patterns of RF signals in a space. So it's similar to Ekahau, Air Magnet Survey Pro, these kinds of tools. And within the tool, they give you a 3D view of the antennas that they support within that tool. And that's what we're looking at here. So on the left, we see a patch antenna, and you can see most of the energy radiating out from the antenna. And this is a top-down view, by the way, if you're looking down on the antenna, if you will. And so we can see it's mostly radiating outward from the antenna. The Omni is radiating all around the antenna. And the internal AP, you get this really interesting pattern here. And that's because this is a 3x3x3 access point. So there are actually 3 really Omni-type antennas inside of this access point. Therefore, you would expect to see a pattern something like this, wouldn't you? You would expect to see what looks almost like 3 spheres or something of that sort. Now, we don't have those 3 perfect spheres because this is an engineered access point, and the antennas have to be placed with consideration of the components inside of the AP enclosure, and other factors as well. But this is showing me basically what that pattern looks like in the AP. Now in this view that we have here, again, I'm looking at a top-down view. Notice the yellow line that is going, in this case, up, but think of that as directionally out. So if each of these are mounted on a wall and you're above that AP or that antenna looking down on it on the wall, think of that yellow line as going out from the wall. And it kind of tells you how this is going to propagate outward in that way. Okay, so this is one way that you can view it with a kind of 3D graph like this. The traditional way we have is with what we call antenna charts, and that's an elevation or azimuth chart, or vertical or horizontal chart. So here on the left, we see what we would see if we're looking at the antenna from the side view of a standard omnidirectional antenna. From the side view, this is the pattern that we see. And this is actually for that same antenna that we've been looking at, the 2 dBi antenna. And you can see how that from the side view, looking at how it propagates upward, it does go up and it does go down, but it mostly is going out. Whereas when you look at it down from the top, you can see it's going out pretty much equally in all directions around that. And to help illustrate this just a little bit more, here we see a superimposed antenna over the charts. So we've kind of flipped the azimuth chart in order to illustrate that it's radiating out around the antenna. And on the left, we have the elevation chart with the antenna there, so you can see how it works in this way. And this is just for learning purposes only. It is to help you understand how you might read these charts and look at them to gain an understanding for how an antenna is actually going to propagate RF energy. This is so important when selecting antennas, and that's why we have covered this information here first. Now, what we also have are then different types of antennas. So here we're looking at physical antennas, the actual components themselves. On the left, we have an omnidirectional antenna, what they might look like. This is more for either an outdoor use or possibly some type of a warehouse deployment or something. You don't see these omnidirectional antennas in indoor office spaces that look like this very often these days. We have a patch or semi-directional antenna here. And then we have a dish antenna. So the omnidirectional antenna generally is going to be placed more central to the coverage area that you desire to cover. The patch antenna at the perimeter aimed inward toward the coverage area. And then the dish antenna is usually used in bridge links. So this is the kind of antenna that we would use for a long distance bridge link because it gives us high gain for the transmission and reception. And it is important to note at this point that when I say high gain for transmission and reception, that an antenna's gain is not unidirectional, it is bidirectional. So the same gain that allows it to push the RF energy further in a particular direction also allows it to receive signals that might be weaker by a low gain antenna. And that high gain antenna, if the signal's aimed at it appropriately, can receive it and process it more effectively. So you gain both in transmission and reception, assuming that you have the benefit on the remote end of the link with equal gain. So for example, if I'm using a parabolic dish like this at both ends of my bridge link and they're aimed well at each other, then I'm going to gain not only on the transmission but on the reception from the other side as well. And so the end result is that I can maintain a better, more stable link over greater distances with these highly directional types of antennas. Now let's talk about this issue of internal versus external antennas. What I have seen commonly is particularly people who are not well trained in wireless. They assume, well, we have this standard AP model that we use, so we're going to use it for everything. And I think this has kind of come along into the wireless space from a lot of other things we've done in IT acquisition. So over the years, if you've worked with things other than networking, like desktop support and server support and things like that, you probably have seen in large organizations, it's common practice to say, we're standardizing on these 3 laptop models for different needs of different users, these 3 desktops for different needs of different users, and these 3 servers for different needs of different servers. And so basically, for the next 3 years, if anyone gets a laptop, this is the one they get, or one of these 3. And they even will often go to the vendors and negotiate deals and negotiate long-term availability and these kinds of things. So what we've seen is some of that can easily trickle into other areas. like access points. So if someone says, well, we're going to use this model of Cisco or this model of Aruba Networks or this model of Ruckus or Aerohive or Mojo, or we could go on and on listing vendors, right? We're going to standardize on this model of AP for our deployments. And then all of a sudden you find yourself in a warehouse or something like that. And what do? You get the APs that you're supposed to use, right? Well, they may simply not be the best AP for that deployment. You might have to deploy 2 or 3 times more APs to get coverage in a warehouse kind of environment than what you actually would need if you were using some better external antenna selections. So external antennas are still beneficial, and I think there's one key point of evidence of this. All the vendors, well, most of the vendors still provide APs that support external antennas. Someone's buying them for some reason. Now, you might argue they're just buying them because they like the pretty antennas that are sticking out. But I think there's more to it than that. And I think that what we would know with wireless and engineering is that we do need external antennas for more than just bridge links. And so let's not think that because APs work well in office spaces that use internal antennas, that is the only kind of selection that we should be making. So let's look at some issues that kind of illustrate this. So first of all, the environmental impact on radiation patterns. So we talked about omnidirectional. So what I've done here is I have put into a wireless design tool an access point using omnidirectional antennas. And you can kind of see that through the early radiation. When you look at the magenta and reds and oranges first coming out of the antenna. And by the way, in this diagram, the AP is on the right where it says Wi-Fi, and it is using an external omnidirectional antenna on the left. So the cable is run through and on the other side of a thick wall where the actual antenna is placed, just to kind of illustrate some things that happen with propagation. So what we have here is we have placed on the floor some highly reflective and very tall filing cabinets. We have a thin wall and we have a thick wall. And what you can see then is that all of a sudden omnidirectional is not omnidirectional. And this is not even as impacting as a real world office environment where you're going to have cubicles and desks and filing cabinets here and there and other large objects throughout that space. So omnidirectional does not mean spheres. We don't see coverage in spheres in any real world environment, except maybe if you place an AP antenna in the middle of a wide open field about 8 to 10 feet off of the ground, where for 500-600 yards around it, there's nothing but open space. Okay, you might see an omnidirectional radiation pattern there. But how often we deploy those? Not very often. They're usually, even if it's outdoor, trees and other items around. So the reality is that things will cause reflection, it will cause attenuation, and you will see that your signal attenuates or moves in directions you may not have expected. So for example, notice that the filing cabinets in this case cause reflectivity that send the signal down and to the right, and you can even see it pushing through that thick wall, so that through that reflection you end up with stronger signal coverage in some areas on the other side of the thick wall further away from the AP. So we see some interesting phenomena that can take place from this. Now this is virtualized, this is in a design environment, this is not real world, but it's done to simply illustrate the environmental impact on radiation patterns. And this is a very non-impacting actually environment that we're looking at right here. So let's look at maybe a little more impacting environment. First of all, on the right, we see a typical office. And already you can see omnidirectional spheres are out the window. Instead, we have the typical amoebas that we see in office spaces. And what I mean by that is they take all kinds of dynamic forms depending on the placement of the antenna, or if it's internal antennas in an AP, the placement of the AP, and then the space that they're actually in and where the walls are. And this particular floor plan is done without any furniture. There's nothing in here except the walls. And so even this is going to change drastically in a real environment where there's furniture and stuff like that. Well, I shouldn't say drastically, it's going to change somewhat. But we can see already a very different radiation pattern in this real world space than what you have in just open spaces. Or let's say it this way, what your antenna charts tell you the radiation is going to be. All that antenna chart tells you is the initial way in which the RF energy is radiated out of the antenna. They cannot tell you how that RF energy is going to propagate through your environment. That is done through modeling with tools like Ekahau, Survey Pro, IBWave Wi-Fi, and so forth. Tamosoft has a Tamograph tool for survey as well. So those kinds of tools are going to tell you that, and actual real site surveys where you go in and actually capture the actual RF energy information in the space. That's going to show you what really happens. So the antenna charts, you're just picking the right kind of antenna you know you need to use for your design. That's not going to tell you exactly how the radiation pattern is going to look in an actual production environment. For that, you're going to need to use the right tools. This is why professionals have professional tools. Professionals use tools that actually allow them to work with the technology, whatever it is. In this case, it happens to be RF, and understand how it is propagating and moving throughout their environment. Now on the left side, you'll notice we have something very different. This is a warehouse with several different storage racks that you can see, a walled area in the middle of the warehouse, a small little break room in the lower right portion of the warehouse as well. And you can really see from this the impact of the environment on RF propagation. These are some metal storage racks that have a solid metal backing behind them between the shelves, so that basically nothing that's put on the shelf will slide over to the other aisle. So there's a solid metal backing and then shelves on both sides in each aisle. And so the end result, as you can see, is getting coverage is quite challenging. And in this case, somebody decided, let's just put in a whole bunch of access points, one in at least every other aisle, in order to get the coverage that we need. Now, to be fair, sometimes you might need this, but strategic choice of directional antennas could also help to reduce the number of APs that are required in a deployment like this. This is what you get with a whole bunch of APs using internal Omni antennas. And so you can see then the result that we get from that decision. Now here you see outdoor coverage, just as an example. It's a basic small office with a couple of access points inside of the building, and then we have a couple of access points to provide coverage to some type of an outdoor area here. And in outdoor areas, you're going to see things like trees and picnic tables and possibly other items that could be there that impact the propagation path. In this case, what we're using is two different semi-directional antennas that are pushing somewhat inward, so they're intentionally mounted such that they don't just go straight out from the building, but they go inward just slightly, so that they provide coverage more to the center area as well as further out in the outdoor space. So with a couple of antennas, we're able to get the RF energy out, if indeed coverage is all that matters in this case, and we're not expecting a mass density of access clients out here in this space. So you can see that this is a perfect example of where omnidirectional antennas wouldn't be as good, for the simple reason that if the only purpose of these APs and antennas is outdoor coverage, using an omnidirectional is going to push more energy back through the wall and into the internal office space. This helps to prevent that from occurring to some extent and give you a little better performance maybe on your internal network than what you would get if, say, the channel 11 2.4 gigahertz AP was omnidirectional and pushing back into the internal space. Now, from these different illustrations then, we can begin to see how the RF propagates through different kinds of environments, and that using different kinds of antennas, even when you're not just building bridge links, can be beneficial. But the reality is we also do have bridge links, and when we create bridge links, we have to make sure that we meet our link budget. The link budget is driven by the needed data rate of the link. So I may define that my link needs to have some minimum data rate. Let's just say 48 megabits per second. So I've said that's what I need my minimum data rate to be. Well, what I'm going to have to do then is look at the antenna gain I'm going to require to stay within regulatory agency constraints and still accomplish the link that I need. So most regulatory agencies, they're going to limit your output power at the intentional radiator and your equivalent isotropically radiated output power in some way. And so it's important to understand those regulations wherever you are in the world. But generally speaking, with an understanding of those regulations and then the choice of the right antenna, you can create links that can span several miles. And of course, to span several miles, you're going to have the antennas mounted very high. You're going to have the line of sight clearance. And line of sight for RF is a little different than just visual line of sight. Just because I can see it doesn't mean I have RF clearance. Remember, light waves, things you see, are much smaller than RF waves, right? And so for that reason alone, we know that we need more clearance than just visual line of sight. Generally speaking, we talk about something called the Fresnel zone, specifically the first Fresnel zone or Fresnel zone 1. And we have to make sure that that is clear significantly. Usually we aim for 80% clearance in order to have a link that can have some variableness in it and still maintain a consistent link. So in these types of links, depending on distance, I mean, if we're just on a campus and we're creating a bridge link that's 100 or 200 feet, we might be able to use patch or panel antennas. But if we're doing a bridge link that is either 1 mile or 1 kilometer or multiple miles or kilometers, then we're going to use higher gain antennas like dish, grid antennas, these kinds of antennas that give us much higher gain, better focus of the RF energy. So this is an important thing to consider when we're calculating the link budget in a bridge like this. It's not just about antenna gain. We have to factor in the output power of the radiator, the loss incurred by the cables and connectors leading up to the antenna gain, and then this really big thing called free space path loss. So as the RF wave propagates through space, it spreads out to a wider and wider or larger and larger coverage area. And as it does, the RF energy available at any specific point in space becomes weaker and weaker. And so therefore we have loss in amplitude as the RF wave travels through space. And we have to factor that into our link budget and make sure that we have the antenna gain and the right output power to accomplish the signal strength required at the receiving end so that we can achieve our data rate. Remember, data rates are driven mostly by this wonderful thing we call signal to noise ratio or signal to noise and interference ratio. Basically what we're doing is saying, is our signal significantly stronger than the noise in the environment? And if it is, we can achieve a particular data rate. So the higher data rates require better SNR, the lower data rates can tolerate lower quality SNR. So this is very important to consider when we're building our bridge links to make sure that we have the appropriate link budget to get the data rates that we desire. And I want to emphasize this again. I say this in just about every webinar where data rates come up. Data rates are not some magical mystery ride into granular modifications in the speed of bits. So in other words, what I mean by that is we're not changing the speed at which we send the RF waves. All right, so higher data rates are not achieved by sending RF waves faster. Lower data rates are not tolerated by sending RF waves slower. We don't speed up or slow down the RF waves. We change the modulation and coding that we're using on the RF waves because RF waves travel at a fixed speed, right? So generally speaking, speed of light in a vacuum, or generally speaking, we just say speed of light. So since they travel at this fixed speed, what we can change is how we're manipulating them to represent bits and how we're sending our bits. Are we sending more actual data bits and fewer redundant bits, or are we sending more redundant bits and fewer actual data bits? So that's the coding part, and then the modulation is how we're actually manipulating the wave to represent bits so that we can represent 2 bits or 6 bits or more depending on how we're modulating this information. So the data rates are fixed, meaning there are specific data rates that are supported. That's why very early on we had 1 or 2 megabits per second, right? We didn't have somewhere between 1 and 2 megabits per second. We had either 1 or 2. Then we added 5.5 or 11. So now we had 1 or 2 or 5.5 or 11. And we also, with 11A, of course, added in, we have 6 or 9 or 12 or 18 and so on, right? And it's still true today with 802.11n, 802.11ac. We have specific data rates we can go to, and we go to those data rates by changing the modulation encoding scheme that we're using. Okay, so that's important to understand. Therefore, I need the signal quality required in order to use a particular modulation encoding scheme. That's really what I'm doing when I say I need this data rate. I'm saying I need the signal quality required to be able to do the modulation encoding that gives me that actual data rate.